Good day, it's Dr. Reiniglin here, EGN3443, Module 7, Statistical Estimation. And we're going to talk about estimators, confidence intervals, tolerance intervals, and practical applications of how we're going to use them. So first, we're going to talk about the concept of statistical estimation. What is an estimator? What are point estimations? And what are interval estimations? I've got some definitions up here, but I've got some definitions that I put together that I'd rather read that are better for this. First, an estimator. Okay, an estimator is really a rule or a function. Okay, it's part of a process of getting an estimate. It uses sample data, and it's used to estimate an unknown parameter of a population. It could be the mean, could be any parameter of a population. Okay, we have to do this because we don't necessarily always know the actual values of a population. We do it through samples. And the estimator is the rule, but in our cases, most cases we're going to look at a function. So we're going from sample to population. The estimand, which we don't use that term very often, but it's the precise description of what we want to measure. Okay, and the precision is important. Okay, being able to define exactly what it is that you're measuring. Now, in many cases, that level of precision is relatively easy. We may be wanting to measure the height, the width, the what, some measurable parameter. And the estimate is that specific value that we calculate, okay, from a sample that we use to approximate the same parameter associated with the population. Remember, sample, population. So the estimate is exactly what we say it is. Now, mostly we look at things like a population mean or a proportion, and we're going to cover both of those. The concept of statistical estimation is where we want to actually determine the characteristics of a population from incomplete data, which essentially is saying we're doing it from samples. So, how do we do this? We define the properties, we evaluate the performance of the estimator, and we consider how robust the estimates are. I mean, it's not really there's no magic here. It's just saying, hey, you got to look at it and understand how well you're performing with the estimates, with the estimation process. Now, good estimators. Remember, we're talking about the function. We're talking about the rules and functions associated with making an estimation. Okay, one is unbiased. An unbiased estimator so basically an estimator is unbiased if the expected value is equal to the population parameter, the actual parameter of the full population that you're doing. So if you're looking at a sample mean, the sample mean is a good unbiased estimator of the population mean, then it is unbiased. It would be a good estimator. How to look at the different properties. Okay, efficiency is also a property that you can look at. We've looked at unbiased. Now we're going to look at efficiency. And if you have an unbiased estimator, the most efficient estimator is the one that has the smallest variance. Now remember, the estimator is the rule or function of what you're using to come up with the actual estimate. Okay, so in the case of looking at the efficiency of the variance efficiency is essentially the variance of the sample divided by the minimum possible variance. You can do a calculation of that. One of the estimators that's used a lot is the maximum likelihood estimator. We're going to talk about that in a minute, and you'll see that there's a process involved here. And the last of them is consistency. Looking at the properties of good estimators, that the estimator will converge to the true value of the parameter as the sample size increases. So the bigger sample you get, the closer it gets to the actual parameter, the population parameter that you're trying to measure. That kind of says common sense. You should get a better value from an estimate using a sample of a larger number of n, bigger n. Okay, now let's look at an estimator. The most commonly used estimator is the most common process is the maximum likelihood estimation. So the first thing that we do in this is we have the likelihood function. Now, you're not necessarily going to ever go through this first step, construct the likelihood function, because the likelihood function, you're going to be doing distributions that you're doing estimation of where you already know the likelihood function. Okay, this will be very obvious when I give you an example. Then you take the natural log of that likelihood function. Okay, this is just the MLE process. You get the likelihood function, you take the natural log of the likelihood function, and then you differentiate with respect to each parameter. Now, the parameter that you're differentiating with respect to is the parameter that you wish to estimate. And you set the derivative to 0 and you solve. So let's just take a really, really simple example. The likelihood function for the Bernoulli distribution, which is the L of P, which is the likelihood function, is P to the x times 1 minus P to the 1 minus x. We take the log of that, which is what I'm not going to go through the math here. And then you differentiate that function, okay, with respect to the parameter that you're estimating. Now, in the case of the Bernoulli distribution, remember the Bernoulli distribution was a binary. It was able to do samples that either had, were true or false. The MLE gives you the sample mean. So the estimate, the MLE estimate, is the sample mean for a Bernoulli distribution. Well, that's pretty easy. That's not massive challenge at all. Okay, this was the process. Now, you're not going to create your own likelihood functions in this class. You're going to do that. You can do that at the graduate level. I had to create likelihood functions, go through this entire process for some of the distributions that I used back in the days when I was in graduate school. I haven't done it since. Well, actually, I take it back. I have done it, but I've done it as a faculty member. Okay. This one, however, you're going to be able to simply look up the MLE for pretty much every distribution that we're going to do. Now, we use it in a lot of different places. Okay, MLE is very, very common. Now, another piece, confidence intervals. Okay, now let me go back one more second. This example was how we get the MLE, the maximum likelihood estimator for a specific distribution, and you're going to see them for other distributions. But now we're going to have to move forward with confidence interval. And confidence interval is saying, hey, and you're probably familiar with confidence intervals. It's that range of plausible values, and I'm going to use that term plausible, for a population parameter, and you specify the interval. Okay, and the confidence level is very commonly like 95%. I'm 95% that it fits inside of these values. The components that go with this are sample mean, critical value, population standard deviation, and sample size. For this basic example here of confidence intervals, I can show this with a simple calculation. If I have a sample where I've got a mean of 50, a population standard deviation of 10, a sample size of 36, and I'm going to use a confidence interval of 95%. I want to know what's that range of that sample mean that I can be 95% confident it lies within that specific range. Well, we find the critical value, the equation. Remember, we're going to go back. I'm going to go back to the equation. Let me see if I got that. I want to pull back that slide. Okay, x bar, that sample mean, plus or minus z of alpha over 2 times sigma divided by the square root of n. That alpha, well, let's go and let's calculate that alpha. 1 minus, remember, 95% confidence interval, so it's 1 minus 0.95 divided by 2. We're looking at both sides. So it's z of 0.025, and that's equal to 1.96. We actually use that enough times that you are going to probably use, that you're going to get familiar with the 1.96 because 95% is used so often. We calculate the margin of error, 1.96 times the 10. Now remember, that was the population standard deviation divided by the square root of 36. That was the sample size, it's 3.27. And 50 plus or minus 3.27, or 46.73 divided to 53.27. That interval, 95% confidence there. Now, you can do this calculation as a relatively easy calculation to do by hand. It's not a hard equation. However, most of the time, you're still going to go ahead and use Python because in this class, you're required to actually plot those up. But you've seen the process and the most important thing, the parameters that you need to do this. So, what affects it? Sample size has a large effect, and the confidence interval that we choose has an effect. Okay, the shape of the distribution will have an effect. We're really talking about, in this case, we're looking at something that approaches a normal distribution, especially as you have an increase in sample size, basically saying as we increase the sample sizes of the different samples that we take, okay, the means of those different samples are going to have a normal distribution, and it allows us to be able to do this calculation relatively easily and give you confidence. Because what we're really saying is that this sample is going to have this parameter value, but you're also looking at, if you took another sample, it's going to give you a confidence interval, and you're actually expecting all of those confidence intervals to also be within, that any sample that you take will have a number within that confidence interval with that level of confidence. It really lets you apply and say, how certain are you? I'm 95% certain, I'm 99% certain it's in this range. Now, we're also going to use this for proportions. Okay, remember that a proportion, we talked about it way back in chapter 2. I don't think we've even used it since, but it's the fraction or percentage of a whole with a specific characteristic. It's basically saying, hey, if I poll 20 people, 100 people and say, do you like or not like ice cream? And 89% say that they do that, that's the proportion would be 89% of that 100. That would be the actual from that specific sample. Okay. And you can do the same thing that we just did for a proportion. Now, I've got a sample that I created for this class. Instead of doing it by hand like I did in the last example, I wanted to demonstrate using Python. And the reason being is that you're probably going to be using Python a lot. So in this case, you survey 200 people. It doesn't even matter what you're asking in the survey. And 130 of them say yes, and 70% say something else. You have an N, 130. You have the number of people, the number of people that were successes, 130. The N, which is 200, that's the number of observations. The confidence interval, alpha 0.05. And we're going to say that this is going to use the normal method. Most of the different things that you would be using the normal Remember, that's making the assumption that the sample sizes are sufficient so that the sample means, or whatever the sample measure it is that you're looking at, would approach a normal distribution. That was back to central limit theory back there in 6. We now, what I'm demonstrating here is that using stats model, okay, you could just say import stats model, but then you'd have to actually put the .stats, .proportion confidence interval. By saying stats model, .stats.proportion is SMP. You can just say the equation down here is SMP proportion underscore confidence interval. That's the name, that's the function name for specifically doing proportion intervals, confidence interval, and proportion intervals, which has the 4 parameters, which I just told you that they are. And in this case, you can actually get what the confidence interval is for this. Remember, it was 65% if you look at 130 over 200, and the 95% confidence interval is between 58.4% and 71.59%. Now, tolerance. Okay, where we were looking at proportions and we were looking at samples that were comparing against specific quantities, tolerances especially in manufacturing, are really, really important. And because what they do is they allow you to go and develop levels of confidence for future observations. Tolerances are important because you're saying, okay, as I'm producing something, based on samples that I've taken of the production process, I have developed a confidence base, or a tolerance is what we're calling it, that says in the future we're within these specific parameters, or what we're going to say tolerances. Our manufacturing process is within this tolerance. Now, I do go over that there's multiple types, and non-parametric, I just need you to know that it exists. Okay, non-parametric tolerance intervals don't make assumptions about the shape of the distribution, and they're relatively complex mathematics to deal with. So we just dealt with a confidence interval, which estimates a population parameter, like the mean, which is the one that we just did, okay, while a tolerance interval estimates the range within which a specific proportion of the population is going to fall. That's important in manufacturing because you're going to want to be able to say that X percentage of the population of parts are going to fall within this specific range inside of that tolerance interval. So a good example would be saying, for a confidence interval, a 95% confidence interval for the average height of students in a school might be 5.5 to 5.7, saying that you're 95% confident that the true average of the height, okay, of those students that you sampled are within that range of 5.5 to 5.7. Tolerance is a little bit different. Provides a range that is likely to contain a certain percentage of the population's value. For example, in this case, we've got the 95% of 90%, which means that you're 95% confident that 90% of the population values are going to fall within the tolerance. Now, that is important because you have those two parameters. So suppose we wanted a tolerance that had 99.99% of the population falling within that interval, and you want to know that you're 95% confident that that population values will fall within that. That's a different thing, not altogether, but it is a different thing. Tolerances being important in this scenario. Part specification, quality assurance, and process variation are the 3 biggies inside of engineering that you do with this. And you can compare the 3. I gave you some comparisons, but the big place that you're going to be using that tolerance is going to be manufacturing specifications. You still use confidence interval inside of manufacturing because you may have to figure out the strength of material. And you do it from samples and you get the mean, and that's a confidence interval. And you know what a prediction, you know what an estimate is. Okay, so we're going to basically wrap this up at 20 minutes here. I'm really hoping that you guys got all this because there are some nuances, and anytime there's nuances, you got to deal with it. But we did talk about estimation. We talked about the MLE estimation, maximum likelihood estimators, okay, which actually that's the name of it, maximum likelihood estimator. It's an estimator that's called maximum likelihood. We talked about confidence interval for samples to a value and proportions. You can also do comparison of proportions, and we also talked about how we can take this whole thing and go forward into the developing tolerances in manufacturing processes and where we can use tolerances. Okay, let's wrap this baby up. I'm hoping that you all got this. You're going to have some